All right, it's my pleasure to introduce now Professor Izzet Coskun. He's going to talk about algebraic hyperbolicity of hypersurfaces and line type conjectures.
Well, thank you for the invitation, and thanks for everybody for being here. Okay, this will be a hybrid talk. Hopefully, everybody will be able to follow it. Let's see how this goes. So I'll talk about algebraic hyperbolicity of hypersurfaces and line type conjectures. And everything that I'll say that's new is joint work with Eric Riedl. And in fact, most of it is work that's already a few years old. But so let me start with an introduction. It's hard to follow Professor Sue, but maybe I'll repeat a little bit what he said. So what's the background and the motivation? So, the first, if we look at the case of curves, if x is a smooth curve of genus at least 2 over the complex numbers, then the universal cover of that by uniformization is the unit disk. In other words, if I look at the universal cover, then you get the unit disk. And in particular, such a curve admits a hyperbolic metric with constant curvature equal to -1. And then, one of the greatest theorems of the 20th century is Folting's theorem, which says that if you have a smooth curve of genus at least 2 defined over a number field, then over any finite extension of this number field, this curve has only finitely many points. For instance, if you have a higher genus curve defined over the rational numbers, and there are only finitely many rational solutions to that points on that curve. And naturally the question arises is how do you extend this fantastic theorem to higher dimensions? And Lang naturally asked this question: is what should we do? Like what properties of curves should we take such that we can hope to extend this theorem in number theory to higher dimensional varieties? And Lang, sort of isolated this question of having a hyperbolic metric. So, and then the usual analog of the hyperbolic metric that you put is called Kobayashi hyperbolicity. So let me maybe briefly recall how that goes. So what you do is you take your manifold X. So let me see whether we can do this. And I don't know whether people on Zoom can see the, they can't, but okay. So I wonder whether it's better for me for the people on Zoom than to do like this. So let's take our complex manifold X, and then we want to define some distance between 2 points, P and Q, on X. So what you do is you take 2 pointed disks and start putting them in your manifold. So maybe the first one is this one drawn in red here. Maybe let me go over it in pink, right? And then maybe the 2 points go to that, and then you take the next one, and then the 2 points go to that, and so on and so forth. You take a chain like this that go from P to Q, and what you do is you sum the hyperbolic distances between the 2 points, and then that gives you some sort of distance between those 2 points. And then what you do, of course, is you take the minimum possible over all such disks. Okay? And so you can think of this as some Kobayashi hyperbolic distance. The only problem is that that might not be a distance. It's in general only a pseudo distance. But maybe before I go on that, is the definition clear? So what I do is I take the 2 points, put the disks, 2 pointed disks, just sum the distances and make it as small as we can. Okay? The problem, is that it may sometimes be 0. So let's look at an example. For instance, if I take the complex plane, say that I want to find the distance between 0 and 1. So what I need to do is I need to take 2 pointed the disk and put it in 0 and 1. But you see what you can do is you can take the disk with, let's say, the point 0 and 1 over r, and take this disk and multiply it by r. And then if you do that, you get like a pretty large disk. Maybe let me draw it like this, where the points go to 0 and 1. But the distance between 0 and 1 over r become arbitrarily small as we make r get large. So that you see that the distance between any 2 points in C in this sense is 0. So you see that it's not quite a distance, so it can be degenerate. And so maybe here's the conclusion of what I just explained, is that if you have a non-constant map from the complex numbers to your manifold X, right, then the Kobayashi pseudo distance between the points in the image have to be zero, judged by this construction. And then the natural definition then is that a complex manifold is Kobayashi hyperbolic if the Kobayashi pseudo distance is actually a distance. And because of this property that if you have a map from C to X, then the Kobayashi pseudo distance cannot be a distance, right? You have this other notion that says that, which is called Brody hyperbolicity. Again, Professor Hsu mentioned all these concepts. And Brody hyperbolicity means that the only non-constant holomorphic map, the only holomorphic maps from C to X are just constant. So you don't have any non-constant entire curves in your manifold X. And just this example we discussed says that if you are Kobayashi hyperbolic, you are Brody hyperbolic. And then the amazing theorem of Brody, it's a really nice theorem, that the converse of this is true if X is compact. So if you have a compact complex manifold, the Kobayashi pseudo distance is a distance if and only if there are no non-constant entire curves in X. And let me caution you that people often also talk about Kobayashi hyperbolicity of non-compact things like complements of hypersurfaces and things like this, right? This equivalence is not true for non-compact manifolds. For non-compact manifolds, Brody hyperbolicity does not imply Kobayashi hyperbolicity. And this is a cute example, so I might just as well give it to you. So basically what you can do is that take a disk and then say you have a family of disks at the origin become like the entire complex plane. Okay, if you did that, right, then this thing would not be quite Brody hyperbolic because you have the entire complex plane. But then, just since you don't care about compactness, throw some stuff out so that you make the central fiber also Brody hyperbolic. You can, for instance, toss out over the central fiber. Let's write it here. Over the central fiber, you can toss out like things that are bigger than one, norm bigger than one, or something like this. Or you could really only omit 3-4 points or something like this. You can do this example algebraically too. But then what happens? The resulting thing is Brody hyperbolic because you see, if I had a non-constant map from C to this domain, right? Let's try this again. From C to this domain, right? I can compose it with the projection to the Z coordinate, right? And that composition is a holomorphic map from C to a disk, and by Bouville has to be constant. So that means that this, whatever this map is, has to lie on one of the fibers. But you see, all of the fibers are disks. All of the fibers are disks, so that has to be constant as well. So you see that this is Brody hyperbolic, but it's not Kobayashi hyperbolic. I mean, essentially what it does is that there is secretly a C there, and you remove the, some set out of it. So what you can do is that if you are at the central disk, right, what you can do is you can go a tiny bit epsilon out of it. You say that you want 2 points on the central disk over Z equals 0. You can just go a little epsilon distance out of that disk. Then there's a very large disk in there, so that those 2 points are very close to each other. So that you see that the distances between any 2 points in the central disk are 0. So these kinds of things can happen if your manifold is not compact. All right, so that was a little aside, and let me make a little remark. You see, the universal cover of an elliptic curve is the complex plane. And more generally, the universal cover of an abelian variety is Cn. So in particular, if you are Brody hyperbolic, if you don't have any entire curves, then if you have a projective variety, right, that's Brody hyperbolic, then this projective variety does not contain anything like rational curves or elliptic curves or abelian varieties. And much of the motivating, much of the interest in the subject comes from the following conjectures due to Lang and Green and Griffiths. So I'm going to lump them all into one big conjecture, and let me sort of, can I give it all in one? Almost. Maybe if we move this. All right, that doesn't help that much. All right. So it says the following thing. So suppose that I have a smooth projective variety of general type. And let me remind you that general type means that there are enough sections of the pluricanonical bundle that you get a mapped projective space of the same dimension as X. So in other words, the space of pluricanonical forms grow as a polynomial of m to the dimension of x. So that's what general type means. So the conjecture is that if you have a variety of general type, then there exists a proper algebraic set, which typically goes under the name of the Lang locus, such that the images of non-constant maps from rational curves in abelian varieties are contained in this proper algebraic set. And more generally, using Green-Griffiths conjecture that says that the images of non-constant maps are contained in Z. Of course, 2 implies 1 is stronger. And the complement of this proper algebraic set is Kobayashi hyperbolic. And finally, the number theoretic analog of Folting's theorem, Mordell's conjecture, is that if X is defined over a number field, then outside of this proper algebraic set, there are only finitely many L rational points for any finite extension of your base number field. So maybe let me see whether I can get that in the whole page. And question? No. Okay. And this is the main set of motivating conjectures in the field. Maybe a few remarks about these conjectures. There are several basic examples that are known, right? So the first is if you take a product of curves of genus at least 2, then putting together Folting's theorem for the curves, then these are hyperbolic and satisfy all of the conjectures. And then the other part is what Professor Xu explained in the past hour, is that there are deep theorems of Folting's on subvarieties of abelian varieties that do not contain translets of subtori. But there is one aspect that maybe I should stress. Like for instance, if you take an abelian variety, then its universal cover is Cn. So what you can do is you can take sort of a random C in the Cn, and if you project that back to X, it can very well happen that that's the risky dance. So that the closure of an entire curve might be bigger than one-dimensional. It could be dense. So this is the kind of thing that gives a lot of trouble for algebraic geometers, where you're like, what is that? So like in some sense, right, the problem has an analytic aspect and an algebraic aspect. Like and the Mays idea was basically to isolate the algebraic aspect, and so he makes a new definition which is called algebraic hyperbolicity. And most of the talk will be about algebraic hyperbolicity and this algebraic aspect of the problem. So now let me tell you what algebraic hyperbolicity is. So maybe before I do that, are there any questions? All right. So now, what's algebraic hyperbolicity? So suppose that you have a smooth projective variety of the complex number. And then so we say that X is algebraically hyperbolic if any curve on X has geometric genus G that satisfies the 2G minus 2. I'm not sure that this 2 looks so good. Let me make sure that this is the 2. 2G minus 2 is epsilon. So X is algebraically hyperbolic if there exists some epsilon greater than 0, such that for any curve on X, the geometric genus of X, or the geometric genus of X satisfies 2g minus 2 is this epsilon times the degree of C. Right, so there is a universal constant epsilon such that for any curve, the geometric genus 2g minus like the geometric genus of any curve satisfies 2g minus 2 is at least epsilon times this degree of C. And the way you should think about this is that maybe one way of saying this is that as you look at your curves on this manifold, then there's some control over the singularities relative to the degree of this curve. All right, so now let's just observe something. So in particular, you see if I have an algebraically hyperbolic manifold, right, then there can't be any rational or elliptic curves on this manifold, because if the genus is 0, then this side, the 2g minus 2 becomes minus 2, and the degree of a curve is always positive in projective space. So this side, so what's this side? So this is the right-hand side, I guess. The right-hand side here is always strictly positive. So if you had genus be 0 or 1, then the left-hand side would be negative or 0. So you see that that cannot happen. Okay, so algebraically hyperbolic varieties do not contain images of rational or elliptic curves. In fact, Domain proves that Kobayashi hyperbolicity does imply algebraic hyperbolicity, and he conjectures that the converse is also true for smooth projective varieties over the complex numbers. But that part, of course, is wide open. I mean, I don't even know whether people believe it or not. So, all right. So let me maybe pause the definition of algebraic hyperbolicity before I go on. Again, what we want is there to be a bound, a lower bound, some epsilon, such that the epsilon times the degree of the curve should always lower bound the 2g minus 2 of the curve, where g is the geometric genus. All right. Any questions? Yeah.
There's some work on the bound of this epsilon, like it kind of tells what kind of degree is the first that will appear, right?
That's right. I mean, and yes, we will. I mean, that will be part of the talk. Yeah. Yeah. I mean, yeah. I mean, there are various ways that you can formulate this. I sort of took it to be embedded in projective space, and you'll see that I don't need to do this. I can define this with respect to any ample. It turns out that the definition does not depend on the ample. If there's an ample for which this holds, and for all the amples that hold, and so on and so forth. And then the epsilon very much depends on which ample you take and things like this. All right. So what is the problem with all these notions? You see, the problem in general is that it's very hard to show a variety is hyperbolic, as Professor Hsu explained. For Kobayashi hyperbolicity, there's been a lot of work, pioneered by Hsu, Demey, and work by many others. What was that? Too large to list here, but and based on ideas dating back to Bloch, as Professor Hsu explained in the past hour. There is one thing that does happen here, and that's if X is a smooth projective variety with ample cotangent bundle. If the cotangent bundle of X is ample, then X is hyperbolic. And of course, the technique usually involves things like, weakening this condition and constructing various jet differentials and so on and so forth to restrict the loci where entire curves can lie. So you see, one thing that we do know is that by results of Brockbeck, on Doshi and Deng, that a general complete intersection of degrees d1 dc and pn of dimension. So if the dimension is less than or equal to its codimension, and the degrees are really large, right? Then the cotangent bundle of a general complete intersection is ample. So in particular, such a variety is algebraically hyperbolic. So as far as I know, the bounds are the best bounds are, I think, due to Deng, and they are of the form like 16 times the codimension squared times 2n to the 2n plus 2c or something like this, right? If you want to make your codimension be a little bit larger, if you make c be twice the dimension roughly, then you can really improve these degrees to to essentially linear. And in fact, if n gets really large, then these things become 3, right? If I make n really large. So that, so if you look at complete intersections of high codimension, then the cotangent bundle of general ones, the cotangent bundle becomes ample. So we know that those kinds of things are hyperbolic. But I mean, here actually there is an interesting question that I don't know the answer to. So maybe somebody, maybe a grad student or somebody can work on it. So in particular, what this says is that if I take complete intersections of cubics, as long as my dimension is large, small compared to my codimension, then such a variety as if you take general cubics, it's hyperbolic. Its cotangent bundle is ample. I don't know, but I would expect the same to be true with quadrics, but I don't know how to prove that. I mean, maybe somebody has a counterexample, or somebody has an idea. But the way this form works, because there's this +2 there, like 2, you can't go down below 3. But this certainly happens for curves, right? I mean, you have to be careful. If you have a conic in the plane, the cotangent bundle is not ample. If you have the intersection of 2 quadrics in P3, that's an elliptic curve, so the cotangent bundle is not ample. But by the time you get to P5 and you take the intersection of 3 quadrics, then you're fine. So I'd expect that to also hold in higher dimensions, but we don't know how to do that. Cubic, we can do that, not quadrics. And anyway, but you see, the kind of questions that we are interested in have to do with hypersurfaces, and the problem with hypersurfaces, or more generally, complete intersections whose codimension is less than its dimension, those will never have the omega x be ample. So like you can't use this kind of argumentation. But let me say that, the focus of the rest of this talk will be entirely on algebraic hyperbolicity. And just like hyperbolicity, deciding algebraic hyperbolicity is also very hard, but it's slightly easier. All right, so let's talk about algebraic hyperbolicity of surfaces. And as Professor Hsu explained in the past hour, these results go to Ein, Clemens-Rahn, Voisin, Pacienza, and basically they say the following thing. Suppose I have a very general hypersurface in projective space, and here I want the dimension to be at least 3. Then if the degree is bigger than 2n minus 3, let's say it like this. If the degree is bigger than 2n minus 2, then the very general hypersurface is algebraically hyperbolic. In fact, if you make n at least 6, then you can lower it by once. The degree is strictly bigger than 2n minus 3, then x is algebraically hyperbolic. And this is an almost sharp theorem. So let me mention that recently a student of Eric Riedl, Warren Young, showed that the algebraic hyperbolicity of the very general optic fourfold, in other words, degree 8 hypersurface in P5. And then on the other hand, every hypersurface of degree less than or equal to 2n minus 3 contains a line. So what that means is that such a thing cannot be algebraically hyperbolic because there is a rational curve in there. So that you see that for algebraic hyperbolicity of hypersurfaces in Pn for n at least 4, the only case where we don't know whether the very general hypersurface is algebraically hyperbolic is the sextic threefolds, the case n equals 4 and p equals 6. I mean, I would expect in that case the very general one to be algebraically hyperbolic too, but you know, maybe we're wrong. So, all right, and then what happens when n equals 3? The story is a little bit different, and then you know, again, these are results of Ein and Shu, with the final case of d equals 5 being due to Eric and myself, where if you have a very general surface of degree at least 5, then x is algebraically hyperbolic, and there again is completely sharp, because if you have a surface of degree 1, 2, or 3, these are rational surfaces, plane, the quadratic surface, and the cubic surface. They contain plenty of rational curves. When d equals 4, that's the special case, that's the K3 surface, and K3 surfaces contain plenty of rational curves and loci curves. They're not going to be algebraically hyperbolic. So this is completely sharp. So maybe since this is a lecture series about the positivity of the cotangent bundle, I thought that maybe I'd explain at least a few ideas that go into the proofs to see like how it's related to the positivity of the cotangent bundle. So this follows from the following theorem, right? So suppose that you have a very general surface of degree at least 5, then the geometric genus of any curve in X of degree dk satisfies the following bounds. And then what I should say is that, like Shu had similar bounds. The main improvement is this additional plus k that allows you to handle the quintic surface case. So in particular, if you want to work out what 2g minus 2 looks like, it looks at dk times d minus 5 plus k. So for all hypersurfaces degree at least 6, you can take epsilon to be d minus 5. For degree 5, you have to take it 1/5. Yeah, so these epsilons do come up, and you're trying to improve that. All right, so now how does this go? So let me maybe sketch like a few key points of the proof. And so the way these things work is like this. Suppose that you have your surface X and you have some sort of curve. So the problem is that this curve can be really, really singular. Like, we know the class of the curve, we know the arithmetic genus of the curve, but the issue is how do you control the singularities. So the basic idea is that, okay, look at the normalization of the curve. So now we have some sort of smooth curve, right? Here we have some sort of smooth curve C, right? And it's mapping into my X, and X can have all sorts of self-crossings and places where the derivative vanishes and so on and so forth. And what you want to do is you want to bound the singularities of C. So what you do is you have a natural exact sequence. You have the tangent bundle maps to the pullback of the tangent bundle of X, and you have some sort of normal sheaf. And now the key is suppose that the normal bundle, this normal sheaf has some degree alpha. We know what the degree of the pullback of the tangent bundle of X is. So this gives us the degree of the tangent bundle of C, which is related to the genus. So you see, the whole issue comes to giving a lower bound on this degree of the normal sheaf. So that is the issue. If I can bound that, right, then I get some sort of lower bound on G, and then the whole point is saying that this alpha is bounded by k minus dk, and if you can do that, then you get the kind of bound that you want. So the issue is bounding this normal sheaf. Now, how do you do that? So here is the observation. Suppose that you have like some sort of, you have some map from a curve to Pn, right? So you have some curve of degree E. So we have our curve here. Thus it has degree E. And now the question becomes, let me look at the pullback of the cotangent bundle of projective space, maybe twisted by 1. And let me try to bound the line bundle quotients of this. Suppose that I have a line bundle quotient of degree minus m of this bundle. Then the claim is that this the image of this curve has to be contained in a scroll of small d. Right? So there has to be a surface scroll that contains this curve, and the degree of that scroll has to be relatively small. In fact, you can say exactly what it has to be. Now, how does this come up? What you do is, you have the usual Euler sequence. So, the cotangent bundle of Pn sits in the Euler sequence, right? So I have the pullback of OPn of 1 that maps to OC n plus 1 copies, and then I get OC of 1 as the quotient. And now we can compute all the degrees. So, this has degree E, this has degree 0, then this has degree minus E. Now, suppose that this pullback of the cotangent bundle twisted by 1 has some sort of quotient, one bundle quotient, of some degree minus m, right? So then I get some sort of kernel of degree m minus e, which then, through the Euler sequence, includes to this OC of n plus 1, which gives me a rank 2 quotient of this OC n plus 1. But by the universal property of the projector space, the projectivization of this rank 2 bundle, which is the scroll over the curve, now maps to Pn, and it contains this image of the curve, and the degree is computed through these things. Okay. So the key observation in some sense is that if you have a small degree quotient of this cotangent bundle, or the cotangent bundle twisted by 1, then you need to be contained in a small degree scroll. But now you see, a curve typically is not contained in a small degree scroll. So by the Noether-Lefschetz theorem, if X is a very general surface, then the only curves on that surface are complete intersections. So in other words, like the curve has degree d times k for some k, but you see any scroll containing this curve has to have degree at least k, right? Because of so this is like a bonehead bound on this. In fact, it would be interesting. I'll raise a question in a second. It would be interesting to improve this bound, and I'll ask a question in a second. But in particular, you see this gives us a bound on how small the quotients of this pullback of omega of p3 of 1 can be. So the final observation is that this normal bundle of the map F arises as a quotient of this f upper star of omega p3 of 1. So in particular, this gives the lower bound on this normal sheet of F. And this part, comes from the setup of Einwesen, Pacienza, and so on and so forth, where the idea, you see, it's hard to get positivity from just one hypersurface, but as Professor Xu explained, it's better to look at the universal hypersurface, and there you can get the positivity. In particular, you see that you can identify this normal sheaf to the map as a quotient of the pullback of the cotangent bundle twisted by 1. So now putting all of these observations together then gives you this bound that you were hoping for. To where this bound was, eventually gives you this. Maybe let's first go here. First, you get the bound on the normal sheaf of this map, which then gives you this bound on the genus of the curve. And that's how you can get the algebraic hyperbolicity of the very general quantic surface. Maybe I should pause. Of course, I'm sweeping under direct some technical things. Worry about that. Maybe let me pause there and see if there are any questions. If not, of course, the same technique can be applied to hypersurfaces in other varieties as well. So, for instance, Hasse and Hilton started the study of algebraic hyperbolicity of surfaces in various toric threefolds, and Eric and I could give the sharp bounds. So maybe I tell you a few of these examples. Like, for instance, if you look at P1 cross P1 cross P1, they're like, if you look at, they're a surface class, you can express it as A1 H1 plus A2 H2 plus A3 H3, where this H1, H2, H3 are the pullbacks of O of 1 from the three natural projections, right? So then you see X is the very general X in this linear system is algebraically hyperbolic, if and only if, again, this is just up to permutation, if either all the numbers are greater than or equal to 3, or if one number is 2 and all the other numbers are at least 4. Similarly, you can look at P2 cross P1, so such a thing is algebraically hyperbolic. Again, now here a hypersurface has class AH1 plus BH2, where H1 is the pullback of O of 1 from P2, and H2 is the pullback of O of 1 from P1. So here you have algebraic hyperbolicity of the very general member of this linear series, if and only if A is at least 4, B is at least 3, or if B is 2, A is at least 5. And similarly, you can look at the blow-up of P3 at the point and describe what can happen. Anyway, I didn't even bother to write here, but you can do hypersurface cross P1 where you project the spaces. So on and so on. We have fairly sharp answers in all of these cases. So let's ask a few questions here. Like, the natural kind of question arises here. Suppose I have a very general hypersurface of degree D, and I'd like to know for which pairs, E and G, does there exist a curve C and X of degree E and geometric genus G? We do not know the answer to this question in general. Of course, if D, so if you just look at surfaces in P3, if you have a plane, then you can map any curve birationally into the plane. Similarly, if you have a quadric or a cubic surface, then in fact there exists a smooth curve of every genus in such things. For instance, if you want to look at the quadric P1 cross P1, if you look at the curve of type 2 comma G plus 1, then that's a smooth curve of genus G. Similarly, for K3 surfaces, there exist curves of every genus, but the moment D is 5 or more, then not all genera can occur. I mean, in particular, we are saying that you can't have curves of genus 0 and 1, but there are gaps. I mean, you can show that if the genus is large enough, depending on the D, then they will occur, but in low degree cases, there are gaps. And we do not have the classifications of all the gaps. And many people have worked on this thing, including Chiliberto, Zeidenberg, and many other people, but we don't have a complete classification of these gaps. The other maybe I should also say one other thing. So I have a student who recently proved the Q theorem. So, and he asked the following questions, for which, so one theorem that we know is that if you have P3, then you can embed every curve into P3. So he asked which threefolds have the property that you can embed every curve into this threefold. And he proves that that happens if and only if the threefold is rationally connected. It's kind of cute. But I mean, I should stress that there exist curves of every genus here, but not every curve of that genus occurs on these things. So in fact, if that happens, then the surface has to be rational. If you can birationally map a curve into every curve into a surface, then the surface has to be rational. What?
The ghost is rationally connected.
Right, but yeah, I mean, but the previous theorem was for threefolds, but this also that's right. And the other question that arises, what is the smallest degree scroll containing a curve in this very general surface degree at least 5? So the question, there's an obvious guess that you can have, right? So if you have a curve, right, then you take its most singular point and you take the cone over the curve with vertex at that point. And, is that obvious naive guess close to true? I mean, so is it true that, the cone with vertex at the most singular point is C is the smallest degree scroll containing this X? I mean, if something like this were true, then you could significantly improve the genus bound that we give, instead of using the boneheaded thing that, it's not containing the rational curve with a rational scroll of Let me make a few remarks. There has been a lot of work recently by young or early career mathematicians. So Wern Young, a student of Eric Riedl, studied hypersurfaces in Pn cross Pm using similar techniques, and she gave a complete characterization of for which degrees you have, hypersurface or algebraically hyperbolic, except in the case P1 cross P3. A student of mine, Luca Mioranci, he studied hypersurfaces and homogeneous varieties like the Grassmannian, orthogonal Grassmannian, symplectic Grassmannian, and so on and so forth. And then a student of, I believe, Ilton, Sharon Robbins, she studied surfaces and smooth toric triples of the car rank 2 or 3. All right. Any questions? If not, then you can ask the next question, right? So far, we were interested in okay, when is my hypersurface algebraically hyperbolic? But there are ranges where we know the hypersurface cannot be algebraically hyperbolic. So then you can ask the question: then what is this Lang locus? What's the locus that's So even when x is not hyperbolic, one can try to characterize the Lang locus. And let me remind you that the Lang locus is the locus of the image of all these rational curves, or all the, depending on what you are talking about, which context, or the image of all entire curves, and so on and so forth. And again, I will concentrate only on the algebraic hyperbolicity side of it. So no claims about entire curves here. So so suppose that you have a hypersurface degree d now less than or equal to 2n minus 3. As I said, such a hypersurface contains lines, so it cannot be algebraically hyperbolic. But then the question arises, okay, can we understand the Lang locus, at least for algebraic hyperbolicity in this context? And so here is what we can say. So again, let me take my x, and let me look at the locus of lines on this x, the part of x that's covered by lines. Let's call that ZL. So ZL is the locus of the union of all, the closure of the union of all the lines on x. And so then here is the statement. So if x is a very general hypersurface of degree at least 3n plus 2 over 2, then any curve not lying on ZL, on this locus covered by lines, satisfies the following inequality: twice the geometric genus minus 2 is at least the degree of C. In particular, you can say that x is algebraically hyperbolic outside of the CL, so that you can take the CL to be the Lang locus of this hypersurface. I mean, again, I'll maybe emphasize this more as we go along, but it would be interesting to lower this degree 3n plus 2 over 2 and understand what happens. Maybe a natural next step is that if I make the degree a little bit lower, right? If I go below 3n over 2, then I expect then the hypersurfaces will also contain conics. Now you can ask, in some appropriate range, is it true that the Lang locus is the union of lines and conics? Maybe you go one step further, now you start containing twisted cubics. You can ask whether lines, conics, and twisted cubics account for all these things. There are some partial results in this direction in the conic range due to Abe, but it's not this, at least we don't expect these to be sharp. Okay. So maybe finally I can just end with sort of another maybe more algebraic notion of hyperbolicity due to Chen, Lewis, Sheng, and Wazan. So you see the kind of question that you can ask. Suppose you have your x, and then you take 2 points P and Q, right? And now you can ask, are these 2 points rationally Chow zero equivalent? And of course, one way they could be rationally Chow zero equivalent is if there's a rational curve that goes between the 2 points, right? I mean, of course, what could happen is that you can add some number of points to this, some number of points there, and you find the curve. They not yet equal. But one possible measure of hyperbolicity that you can think about is like understanding the loci that are rationally Chow zero equivalent to each other on this hypersurface. And here there is a conjecture, or there was a conjecture by Chen, Lewis, and Sheng. This is Shi Chen, inspired by work of Voisin. And it says the following: if X is a very general hypersurface degree D in Pn, and P is any point, then the dimension of the space of points rationally Chow zero equivalent to P is at most 2n minus D minus 1. This conjecture was proved by Chen, Lewis, Sheng when 2n minus D minus 1 is less than 0, and by Riedl and Yang in general. So again, we can sort of ask, what's the Lang locus or the analog of the Lang locus in this context? So let's maybe define 2 loci. Again, what I should do is let me take my hypersurface X. So I drew my hypersurface as this blob. So here's our X. Right, here's our X. And then there are two loci here that are interesting. So let me look at points. And let me call this V1 points P. So the hypersurface has degree D, right? So if you have a line, right, typically it will meet this thing in D points. But I want to look at the points on X such that there is a line of contact order D. So in other words, the line meets this hypersurface only at that point. Okay? So let's just, Z1 is the set of points P with a line of contact order D at that point. So let me call this thing Z1 for, there is a line that meets this thing only at this point. Of course, the closure of this locus does contain the locus where the line is contained in the hypersurface. And then let's talk about Z2, where, you have a pair of points now, where there is a line meeting these 2 points only at those 2 points. So you have contact of order I at one and D minus I at the other. This locus set like this, of course, is reducible because you can change the I and D minus I to take the union of all those things. All right, so like I look at the set of points where there's a line of total contact at that point, and set of pairs of points where you have the line just. And then you see the kind of question that you can ask, the kind of thing that you can say is the following. So if I have fix a positive K and say that the degree of your hypersurface is at least 3n plus 1 minus K over 2. Then the statement is that the only points of X that are rationally Chow zero equivalent to a K-dimensional family of points lie in Z1. So if I, look at points that are rationally Chow zero equivalent to a K-dimensional family of points, then they have to be these points where you have a line of high contact order. And similarly, if you make the degree be at least 3n plus 3 over 2, the only points rationally Chow zero equivalent to any other point lies in Z2. So, in particular, you see what you learn is, it's a slight improvement of the theorem of Clemens and Run and Hacienda. So, in particular, if you have a hypersurface of degree 3n or bigger than or equal to 3n over 2, such a hypersurface contains lines with no other rational curves. So lines are the only rational curves between 3n over 2 and 3n over 2 and 2n minus 3, the only kind of rational curves you can have on lines. As I said, there are lots of interesting problems that that are completely open here. One is extending this from the linear range to, then you want to say that the next range of cases when you have only lines and conics and so on and so forth. And we do not know sharp results in this case. This is fairly close to sharp, I forget. I think this is sharp if n is even and maybe possibly off by a half if n is odd or something like this. The moment you make it a little bit less, then you have conics on the hypersurfaces, so you don't expect it to be just like this. This is sharp. And the other thing that's open is, of course, extending these kinds of length type locus analysis to other devices and other homogeneous varieties of total varieties and things like this. Maybe I'll stop here, and if there are any questions.